Morning, good afternoon, and good evening, everyone. So today we're going to be continuing our applied linear algebra series, and we're going to go into lecture 7. And here we're going to talk about matrices and linear equations. So just to give a brief background on what this is. So far we've been studying vectors in RD, right? And so our goal in this lecture is to introduce a new family of fundamental objects that are the subject over study in the remainder of the course. Okay? And so when we talk about matrices, well, one of the most fundamental types of problems we encounter in natural and computational science is a linear system of equations, right? So that's one typical thing that we would encounter in linear algebra. I'm just gonna write it out. So here we're gonna motivate matrices through linear equations, and I've kind of done this already, so I might just do a. I'll just do it quick, basically. Okay. So say we have this linear system, and let's say we can convert them to a matrix. There, I said it. Minus x, 3y, minus 2z is 4. Okay, so to solve this, we can use elimination and substitution, right? And so if we do all of that, then we're going to get x is 5 over 12, y is something, 23 over 12, and z is 2 over 3, right? So using the process of substitution or elimination, we can get to this value. But the goal in these next few weeks is to understand how we can generalize and perform this type of operation. And so actually the funny thing is we can write this system as dot products. Okay. So how would that work? Well, for one, we could write it like this. We could rewrite it. So I'm going to say we can do this, right? And for instance, maybe first one, let's try. 1, 1, negative 2, x, y, z. And that dot product is 1. So this is what we've learned, right? We can do a dot product, then we would get a 1. And we can do the same thing for the others. So we could do 3, negative 1, 1, x, y, z. This is 6. Okay. And then lastly, let's just do the last one. So we have negative 1, 3, negative 2. So here I'm just getting the coefficients. And then this is 4. Okay. So this is what we can do when we're rewriting systems. And now solving this is equivalent, right? So this linear system that we just did and solved for it, we can do the same thing here and we should get the same thing for x, y, z. So I'm going to say same thing or same solution. Then why that look like a dollar sign? Same solution as system above. Okay? But now let's actually introduce what matrices are. So based off of this idea, what are matrices? So a matrix is a rectangular array of numbers, and in general, we write R to the m by n to denote the space of matrices with m rows and n columns. So what do I mean by that? Say we have a matrix A, we write it like this, where m is the number of rows and n is the number of columns. And so how that would look like is, for instance, we have this entry, A11, A12, all the way to A1n. This denotes the number of columns. I go down, this denotes the number of rows. AM1 all the way to AMN. And that just keeps going. Okay? That's one way to look at it. Then we have some examples here. I could go through some. This one, let's try. We have 1, 1, -1, 2, 4, 6, 8, 12, 0. This here is a matrix A, 3 by 3, because there are 3 rows and 3 columns. How about this guy? This here is a matrix 3 by 2, because there are 3 rows and 2 columns. Now this one's interesting, but how about this one? This one is 3 by 1, but you could also just say 3, right? And this is actually a vector in 3D. So it has 3 components. Okay? Now let's actually look at a matrix vector product. So do that. So given matrix A, and so I'm gonna generalize it because I'm gonna assume most of you know what this is. And some vector V in our N. Mat vec, matrix vector product, is defined as, so say we have, okay, say we have A multiplied by this. So we just go through that matrix. We go through this one times this vector from V1 all the way to Vn. And this is the same thing as multiplying A11 V1 all the way to A1n Vn. And then we just keep going, AM1 V1 plus all the way to AMN Vn. And maybe a nice way of writing it is a summation from, let's do K, all the way to N. So we do A1K BK all the way to, keep doing the same thing here, AMK BK. So we just wrote it as a summation, and this in return is actually a vector in Rm, where it has m components, 1 to m, right? Okay, I hope that makes sense because we did go over this in my scientific computing series, so this shouldn't be too difficult. So we say that an Mn matrix, M by N matrix, maps an n-dimensional vector to an m-dimensional vector. What does that mean? We say that if we multiply this M by N by an n-dimensional vector, we actually get a new vector with a new size, which is M, assuming M is not N. And so we note that the mat-vec product is only defined for some A matrix M by N and some vector V Rn. And for every vector V in Rk, oh, wait, for, if V is in Rk and K is not N, product is undefined. What does that mean? Let me just write it out. Mat-vec product is only defined if, say we have matrix A, M by N, and we have vector V to the N, and we say that if, let's say my V is some K and K is not N, then product is undefined. Or in other words, this doesn't work. Because we can't do a dot product where we don't have equal number of, we can't multiply something from A to V. Okay? So let me, is there a way to do this? Okay, there's no way here. I'll just give an example. Say we have A to be 1, 2, 3, 4. So this is a 2 by 2. And then we have vector V, let's say in R3. Let me do 1, 2, 3. And I want to know, I meant 3. And I want to know what's the product of this matrix and this vector. Well, okay, we can try and multiply. Let's try multiplying this one. We get 1 times 1. So I'm mapping this one to this one. And then we say plus 2 times 2. So I'm mapping this one to this one. And then, whoa, what do we map to 3? Where is 3? So we know this is undefined. So what I'm saying is that the column of what we're multiplying, the number of columns should be equal to the number of rows. And this is the same, I'm going to say it already, this is the same when we're given two matrices that we want to multiply together. Okay? Right. Let me just go back here. Okay, this one is just saying it in a weird way. We can think of so here they just tell us there are lots of ways to think about matrices. Okay. Right, so here's what I'm just gonna say. There's lots of ways to think about matrices. So one is linear system. That's the most obvious one because we've studied that even before doing matrices, right? So for instance, we have this linear system. Oh, shoot. Easy. I'm just copying from what was discussed in lecture so that I don't get off tracked or sidetracked. Or I forgot what that was. Negative x plus 3y minus 2z equals, I think it was 4. Now we can think of these. So that's one way of organizing it. Another way is through MatVec. I'll do it in ax equals b. And we've probably seen that already in my scientific computing series. But just to review, so again, we do a, and we go through the coefficients of each equation here. Then we say our x vector is going to be x, y, z. And then we say our b vector is going to be 1, 0, 4. So when we go through this equation, we're just saying that we multiply this matrix A by the vector x, and we're going to get B. We're going to get a resulting vector. Okay? So that's how we can look at it. Now, another way to look at it, a matrix is actually just a collection of vectors. And there are two ways to think about it. So let's say we have this matrix and let's do A12, no, not A12, A11, A12, all the way to A1n. How much did he do? Okay, I'm do A21, A22, A2n. Then we keep going Mn, M1, all the way to Mn. Okay. Now, what is one way of thinking about it? One way of thinking about it is looking at these as column vectors. So how would that look like? Well, that would be A1, A2, all the way to AN, where AJs have M components. That's one way of looking at it. We can think of it as columns of vectors. Another way is thinking of it as row vectors. So how this would work is something like one to M, A1 tilde, A2 tilde, all the way to A M tilde, where A J's tilde is R N, Z N. Oh, and then also we think of it as transpose. We're transposing from a column vector to a row vector. Because by default, we think of vectors in this course as column vectors. And so when we transpose them, we will talk about this idea of transpose. When we transpose them, they're going to turn into row vectors. Okay? And so that's how we would like to think of them. And so maybe a new way, so based off of these ideas, a new way of thinking about MatVex, right? So we did think of it as like the sum. So this one here, we thought of it initially like that. Now, there is another way of thinking about it. We could think of it as the dot product of what? Of our column, so the tilde, and the vector that we're multiplying it with. And that's the same for all of them. We go all the way to M. And there we have it. Okay, pretty short, but I hope you guys enjoyed this video, and I'll see you all in the next one.